All right, so we are doing a massive overhaul of probability. So let's get started. 7.1, the basics of probability. So once again, we are going to look at desired over total. That is our probability. So basic probability problem, number one, we are going to do desired over total, which means the number of A situations over the number of total situations will get you your probability that you're looking for. So no matter what the problem's asking you, that should be your thought process for any probability problem. Now, number two, it's asking us what is the probability you land on a purple space. So our desired is going to be purple over total. So purple spaces, I'm going to consider 6 and 7. These are the purple. I'd assume those are the pink. So we have 2 out of 1, 2, 3, 4, 5, 6, 7, 8 spaces. So we're going to do 2 out of 8. So if I simplify that, probability of A is 2 over 8. So I'm going to do 2 times 1 gives me 2, and 2 times 4 gives me 8. There we can see that the 2's here are going to cancel or 1 out each other, so that the probability becomes 1 out of 4, which is 0.25. If we times it by 100 or move the decimal 2 places, we're going to get 25%. All right, next one. Using the image to answer the questions below. So we have a bunch of different colored balls and different types of balls. So let's look at letter A. A says, which color ball is most likely to be drawn at random? Well, we look at this, we have 2 purple, we got 2 orange, we got 1 green, but we have 3 soccer balls. So which is most likely to be drawn? The one that is the most. So we are going to call this soccer balls. Okay, it's not asking for a probability, it's just asking us for an answer. So I'm just going to leave it at soccer balls. My guess is we're going to find probabilities next. What is the probability of drawing an orange or a purple ball? So when we do this, we're going to do O or purple. And the or symbol looks like that. So we're going to do the proper probability of orange plus the probability of purple. And we're adding these together because it's not one thing and then another thing happening. We just want to know, put these 2 probabilities together. So when we look at this, the probability of an orange is 2 out of 1, 2, 3, 4, 5, 6, 7, 8. Oh, that simplifies to a quarter. Probability of purple, same, 2 out of 8, which is another quarter. So if we do orange or purple, we're going to do a quarter plus a quarter, and if we have 2 quarters, we have 50 cents, which is a $50, which in turn is 0.50 times it by 100, and we have 50%.
Can you just keep an eye on the Instacart? I'm gonna put him to bed.
Yeah.
So
Last one. What is the probability of drawing an orange and a purple ball? So if we want to do an orange and a purple ball, we have to know when we can draw one ball and get orange and purple. 0. There's no chance of that actually happening because we're only going to do one or the other. We can't really pick both at the same time. Okay? Braden, thank you so much. Appreciate that. All right. Using the image below, create an event more likely to happen than the probability of T or C. Well, if I look at T, there are 2 of them, and C's, there are 2 of them. Well, just by looking at that, I can see 4 A's right there. So I'm definitely going to do the probability of A, or, and it doesn't matter, anything I pick that's out here is going to be a probability that is more than T or C. And that's because there are 4 choices for T or C, and A alone has 4 choices. Okay? So that automatically makes A and anything else anything else going to be more. So, all right, let's do letter A. What is the probability you pick a T or a C? So probability of T, let's not do or, let's do the right symbolism for it. T or C. So we're going to do the probability of T plus the probability of C. So if we look at the probability of T, we said there were 2. 1, 2, 3, 4, 5, 10, 15 choices. And the probability of C is 2 out of 15 as well. Do the probability of T or C. And we're looking at 2 over 15 plus 2 over 15, which is 4 over 15. Now, this is one where I have no idea what the decimal is. It's 0.267. So this is going to be 0.267 times it by 100, move it 2 spots, and we get 26.7%. Sorry if that's off my phone screen. What event would be more likely than T or C? So we already did this. We said the probability of A or W. So we want the probability of A plus the probability of W. The probability of A was 4 out of 15. The probability of W is 1 out of 15. If we add that together, that's 1 out of 15 equals 5 out of 15. And if we do 1 times 5 and 3 times 5, because 1 times 5 gives us 5, 3 times 5 gives us 15, there is a 5 on the top and bottom. Therefore, it just becomes 1/3. And 0.3 repeating, move it 2 spots, and we're left with 33.3%. All right. Next one, set notation. So now we're putting these things in sets. So if I label everything in set A, so I'm looking at only set A. So what is in this red circle? Well, that's going to be B and C, and we can close that up. Everything in B, we would do the same thing over here, and that would be C, D, and E. Now, label everything in set A and in B. So now we're looking for things that are the same in set A and in set B. And the only thing that is there is C. That's the only thing they both have in common. And then if you do an OR, what you're going to do is combine these. So we have B, we have C. We already have C written, so we don't need to write it twice. But then we're also going to add D and E. Label everything in the universe. So that's everything on our page. So now we have A, B, C, D, and E. That's everything. And when we say everything, we're talking about the dots. Okay. Now, if this is our universe and our set A is B and C, what they're looking for in A complement, that's the little c up here, is everything that is not in A. So if B and C are in A, that means A is not, D is not, and E is not, because that's our universe. What is the probability formula for mutually exclusive events? What is, so that's a OR probability For overlapping, we're looking at an and. Find the probability that a person chosen at random will be a female or a person who prefers an SUV. So for this one, for mutually exclusive, it means there's no overlap. So we're just doing the probability of A plus the probability of B. But with overlapping, we have the probability of A, we have the probability of B, but we need to subtract the overlap because it's getting counted twice. So if we do females and sports utility vehicles, this 135 gets counted in both of them. It gets counted in the females and the sports utilities, and we only want to count it once. So we have to get rid of that overlap between them. So that's where, when we have overlapping events, what we need to do. So find the probability that a person chosen at random will be a female or a person. Oh, wow. That's interesting. Not that I was going for that, but I already talked about it. So we have sports utility vehicle and we have females. So what we are looking at is the probability of a female or, oops, I guess that should be an or as well, my bad. Ooh. So we'll do probability of A or B, and then A or B, but there's overlap here. So F or S, SUV. So we need the probability of females plus the probability of SUVs minus the probability of a female and an SUV because they're getting counted twice. So the females, we're going to do the total females, which is 180, out of our grand total, which is 240. This grand total is used every single time except when we're doing conditional probability. So that's where our condition comes into play. But for the rest of them, you just use 240. The probability of an SUV is 156 over 240. And then the probability of a female and an SUV is 135 out of 240. So now when we set it up, we want the probability of a female or an SUV. We're going to do 180 over 240 plus 156. It's a terrible 6. 156 over 240 minus 135 over 240. So let's see if we can set that up on our decimals. So 180 over 240. We're going to move it over. We are going to add it. Now we're going to do 156 over 240. Move it over, and then we're going to subtract the intersection, which was 135, and we get 67 over 80. So this is going to get us 67 over 80, which when we looked at the percent or the decimal, 0.838. Move it 2 spots and it becomes 83.8%. All right. Number 9, what is the probability that a person is randomly selected who likes math and science? Explain your reasoning. So the people that like math and science means that they're in both circles. And that means we're looking for where the two intersect. So we're looking for the intersection, which is 7, out of our total. Now, when we talk about our total, we're talking about our universe. So that means 9 plus 6 is 15, plus 7 more is 22, plus 7 more is going to be 29. So that is a probability of math and science. Okay? And it's because we're looking at where they overlap, math and science. Use a table to answer the questions. So now we're going to two-way tables. This was 7.2. Use the table to answer the following question. What is the probability that a person has a math background or a chemical background? So once again, this is where you're going to get some overlap. You're going to have the math background here, but you're going to have the chemical background here. So they're crossing each other right here at that 80. So I'm going to do the probability of math or chemical. So that's the probability of math plus the probability of chemical minus the probability of math and chemical. Okay, so math was 254 out of 516 plus chemical, which was 171 out of 516 minus the intersection, which is 80 over 516. So for this one, I'm just going to set it up. I'm going to let you simplify, find the decimal, find the percentage. Really just trying to help out setting these formulas up and solving them out. All right, so we have males, we have females, and then we have total. The last one should always be total. We have short hair, and then we have long hair. Okay, so it says 30 of the rabbits are male, so that means the total number of male rabbits is 30. We have 8 of the female rabbits have short hair, so there's 8 of them that are female and short hair, and then 12 of the rabbits with long hair that are male. So if we have 12 here and we minus that, that means there's 18 of them here, okay? Because we do 30 take away 12, that will leave us with 18. Now, if we have 18 and 8 here, that is 26. Sorry, I missed one. There's a total of 45. I was about to miss something because I needed one more piece of information, and that piece of information was 45, because I wouldn't have been able to finish the table had I not had all this. So that last piece of information I did need, because that got me my 15 here, which gives me my 7 there, which gives me my 19 here. And if you add all these together, they should all come out to 30, 15, 45, 26, 19, 45. We're good. What is the probability that a rabbit has long hair? So we're looking for the probability of long hair. So long hairs, there's 19 of them out of 45. Use justification to support your answer. I would start with the desired over total. And my desired are going to be long hair over total. Emma has 45 rabbits equals the total. That's given information. The problem told us. And then by simplifying some stuff, we discovered that the long hairs are 19. And then we would do substitution into here and then simplify, solve it out, find our decimal, all that good stuff. All right, true or false? In general, a probability of A given B equals the probability of B given A. You can reverse the order and the probability is the same either way. That is definitely, there are some times where it could be true. But more often than not, if they give you that type of problem, you're going to get 2 different probabilities. And the reason being is, what is the probability? Let's say A is red and B is queens. So what's the probability of it being red given that it's a queen? So if I look at queens, there's only 4 of them and 2 of them are red. Now, let's flip-flop that. What's the probability of a queen given that they are red? Well, there are 26 red cards and there's only 2 queens. So that's a much smaller probability. So that's where you really got to pay attention. Okay? All right. What is the probability that a red card is also a jack? So we're looking for the probability of a jack given that it's a red card. So our red cards are our total, and then our jacks are what we are desired. So we want, well, I guess we better put, let's do this. So we're talking about red cards. That's our total. And what our desire is a red jack. Okay? So red cards, if we highlighted all the red cards, there are 26 total red cards because you have 1 through 10, 11, 12, 13. But 2 sets are red. So that's how we get 26. And how many red jacks are there? There's just 2. So this is going to be 1 out of 13 chance. All right, what's the probability that a jack is drawn given that it's a red card? Okay, so you need to understand what this is saying. Once you have a given, that is your line. This means given. So what is given? It's a red card. What are we looking for? A jack. Oh, well, isn't that the same probability that we just did? It is. It's written a different way, but it's still finding the exact same probability. We're trying to make sure that you know when it says given, you've got to draw that line and establish that that's the given. All right, 14. A salon owner noted what types of services its clients requested last week. Here are some results. So we talked to a salon, and it's either a dye, there's either a haircut, or there's a permanent, permanent withstanding appointment. I don't know. Find the probability that it randomly, and maybe I'm just don't know about hair, but maybe it's a perm. And I've always heard it as a perm, so I guess I never knew it was a permanent. Anyway, I don't know. I'm sorry, I'm not more apt on my. What is this? Get rid of this. Can I get rid? Okay, there we go. So maybe I'm just not apt on my hairstyles. Find the probability randomly chosen client requested a haircut given they requested a dye service. So we want a haircut given that they did a dye. Okay? So what was given is the important piece because this becomes our total. Our given is going to be our total. Remember, our desired is a haircut and a dye given that they got a dye. Okay? So a haircut and a dye we can see is 30% out of the whole thing, which is 35%. Now, even though they're percentages, they still work the same way. We could actually do a 0.3 over a 0.35. We could have played that game. We could do a 3 times 10. No, we can't. We can do 6 times 5 and a 7 times 5 for percentages, and we would be left with 6% over 7% or 0.06 over 0.07. At that point, you're playing with the numbers. They all will give you the same kind of decimal answer. Whether I would put 6 over 7, 0.06 over 0.07, or I could have left it as 0.3 divided by 0.35, or I could have left it as 30 divided by 35. All of those play the same game and will give you the same output at the end of the day. So I'm just going to try 30 over 35. It's going to simplify to 6 over 7, which is 0.858 or 857. So then I will put that down. 7.4, independent and dependent probability. What we just finished. What's the definition of independent events and to find the probability of independent events? So the definition means that one probability has no effect on the other probability. So if we wanted to do the probability of A and the probability of B, we just need to do the probability of A times the probability of B and multiply those together. They're two separate events, and the outcome of one does not affect the outcome of the other. Dependent, though, is the first one does affect the second one, because when we do the probability of A and B, we're going to have the probability of A times the probability of B given A actually happened. Okay? So, and remember, what was the probability of B given A? This is where you got to go back. That's the probability of B and A happening over the probability of A. And where did that come up? Let me just backtrack. Let me see if I can find one that we talked about that. Where is mine? Maybe it was back in. No, hold on. Nope. Oop. Oh, maybe we. God, I felt like I said. I guess here we go. Okay, yeah, here we go. So the given is our red cards, and then the top is a red jack. So you have both probabilities, red and a jack. So when we look at that conditional probability, we're talking about a red jack. So it's a red and a jack just over the red cards. So that same kind of idea is going to come out here, where we have a red, or we have a jack and red all over the red cards. Okay. The reason we're going to do this is because we got to play the game with the ands. And this is a conditional probability. It doesn't have an and in it, but this one does. All right. So determine if events A and B are independent. Justify your reasoning. So if I look at this, I can see the probability of A, the total is 5, and then the probability of B is 4. That's already starting to indicate that they are dependent probabilities, because if I pull a sock out of the drawer, which we did that on the worksheet today, and we pull another sock out of the drawer, we only have 4 socks instead of 5 socks total because we didn't put that other sock back. Whereas if I pull a sock and then I put it back, I still have 5 socks to draw from. So it's independent events that are happening. But if I pull a sock out, I put it off to the side, and then I draw another sock, my total has just went down by 1. So what we should be looking at is 16, where the probability of A and B equals the probability of A times the probability of B given that A happened. So let's see if we can make that happen. So the probability of A and B is 1 over 25. And what we're going to see is the probability of A is 2 over 5 times the probability of B, which remember is A and B, 1 over 25, divided by the probability of A, which is 2 over 5. Well, if we looked at this in a different scenario, and if we talked about just the probability of A times, and let's go back to this one right here, what is that? It's the probability of B and A over the probability of A. What happens to the probability of A's on the top and bottom? Don't they cancel each other out? And we're left with the probability of A and B equals the probability of B and A. So it does work out even without the numbers. However, the numbers would definitely guarantee us that these two sets of numbers are equal. All right, so let's look at this one. I'm already sensing that the total is 5. The total is 5. I think these are independent events. So I'm going to do the probability of A times the probability of B. One is 2 over 25 equals 2 over 5 times 1 over 5, multiply straight across, and we would get those numbers to work out. Ooh, a complement or not A. So it's 3/4. So if we took a whole pizza and we cut it into 4s and we said 3 of them, 3 out of the 4 are not A, that means A has to be 1 out of 4. Has to be the remaining piece. Oh, I'm sorry, you can't see that. Slide that over just a bit for just a second. So you can see I cut it into 4s. I colored 3 of them in. That means there's only 1 left for that A situation. Okay. So the probability of A was 1/4. The probability of B equals 3/10. And the probability of A and B equals 3 over 40. Well, that to me, if you look at multiplying these two together, 1 times 3 is 3, 4 times 10 is 40. That's independent probability because I just need the probability of A times the probability of B. And we already know that that is independent events. So these are your independent, dependent variables, but it's really about manipulating the formula. You are going to see this on the test, I promise. So make sure you study that. All right, so back to that game again. I'm going to let you practice that, but remember, the probability of B given A equals the probability of B and A over the probability of A. So I can do the probability of A. The probability of A and B, I'm going to have to figure we're going to have to go back in our tool belt from 7.1, and the probability of B and A equals the probability of B plus the probability of A to find B and A. And then I would take that answer divided by the probability of A. Because isn't this that conditional probability again? Yes, it is. So that's how we would get our final answer when it's all said and done. But this is what's going to get us B and A. Okay? Find the missing probability. All right. So once again, we're going to do the probability of B and A, put it on top, divided by the probability of B, and that, oh shoot, excuse me. So remember, the probability of A given B equals the probability of A and B over the probability of B. Now, if we were looking for the independent events of A and B happening, where they are independent events, that's when we would multiply it again, like based on this formula, but we don't have multiple events. It's just saying here's our one event. So we are going to do 1/10 divided by 2/5, and this solution is going to be A given B. All right, so let's put this into practice because there's a lot of things going on, but I think the more examples you see of this, there are multiple events happening. So she pulls a yellow ball from the bag and does not replace it. Right there, does not replace it is a dependent situation, okay? And now what is the probability that the next ball is yellow? So we are pulling multiple balls out of here. So when we look at that situation, we want two things to happen that are two separate pulls of the bag, but the second one is definitely dependent on the first one. So when we do this, we're looking for the probability of A and B, where that's going to be the probability of A times the probability of B given A happened. And B equals the probability of A. She pulls a yellow ball. So how many yellow balls are there? There are 12. Out of how many total? 3 of the balls are red, 5 are blue, 12, so 8, so 20. Then we need the probability of B given A happens. Well, once I pull a ball out, am I left with 20 balls? No, I only have 19 now. And I pulled a yellow ball, and I don't replace it. What is my next pull? And we want that next pull to be yellow as well, right? What is the probability that the next ball is yellow? So what we need to do is once we take one of these yellow balls out, because remember that's the first condition, we only have 11 left. We can multiply straight across and do all of our normal stuff. All right, she pulls one ball from the bag and then replaces it. Oof, right there. Replaces is such a key term because that's telling you they're putting them back and these are independent events. She pulls one ball from the bag, then replaces it. What is the probability that it is not blue? Oh, okay. So really, she pulled one ball from the bag and then replaces it. What is the probability that it is not blue? So they're only doing one pull. So we want the probability that it is not blue. So this really isn't even an independent or dependent event because there aren't multiple events. It's just one event. How many are not blue? Well, if there are 5 that are blue, that means out of 20, there are 15 that are not out of 20. All right. We did a lot of probability. We finished off with independent, dependent. Before that, we did our... I didn't even put 7. Oh, man. Well, 7.2 was two-way tables. So 11 and 10 were the two-way tables. And then we did conditional probability. Sorry, it wasn't labeled. But this is 7.3, conditional probability. And then two-way tables. And then basic probability. Set notation. Mutually exclusive and overlapping events. There was a lot in 7.1. It was really kind of laying that foundation, which was why there were so many problems on 7.1. Well, I hope you got your questions answered and you are successful. I would appreciate a like, maybe even a follow. Would be very much appreciated. Otherwise, have a blessed night, and we'll catch you next time on Math Dragon Moments.